Howdy. This video is on nuclear power. The strengths of a nation's economy and the living standard of its people depend on relatively inexpensive power. A lot of pollution, for example acid rain, greenhouse gases, is produced during the production power. Waste from nuclear power plants stays radioactive for tens to hundreds of thousands of years, and there's always the possibility of an accident. As a voter, you may have to decide if you want more nuclear power. After watching this video, you should be able to identify the advantages and disadvantages of nuclear power. You should be able to describe the relationship between nuclear power and nuclear weapons. You should understand that both nuclear power plants and nuclear weapons use enriched uranium or plutonium, but the level of enrichment is different. You should be able to describe how a nuclear power plant works. In 2011, it was projected that there would be a 50% increase of global energy use by 2035. And so you can see that the industrialized nations, their energy use was projected to be increasing slowly, but the non-industrialized nations would have a greater need. And so the question is, how will this energy be produced? And so currently, U.S. energy production and demand, 83% of supply is fossil fuels. That was in 2011. And so on the left, you have the energy supply, and on the right, you have energy demand. And so the biggest supply would be petroleum. Nuclear is small at 8.3, renewable 7, coal 20, and natural gas at 23%. And the demand, you're looking at transportation, residential, commercial, electricity, residential, industry, electricity, industrial, electricity, commercial. So I'm not sure how they define some of these. And I think energy of supply may also include like for transportation. Now in 2009, the U.S. electricity generation was 70% fossil fuels, 20% nuclear. By 2022, it's kind of interesting. The fossil fuels actually went down to 60%, and the renewables went up to 22%, and nuclear was pretty steady at 18%. And so it's kind of interesting that we're seeing a switch away from fossil fuels and more to renewable in terms of electricity generation. Now, natural gas has advantages of it's relatively cheap, relatively accessible, burns cleaner than coal, easy transport. You can just use pipes. The disadvantages is it produces greenhouse gases and there is a limited supply. Coal has the advantage that it's relatively accessible, relatively cheap. The disadvantage is that, again, it produces greenhouse gases, limited supply, emits SO2 and SO3, which produces acid rain, also emits mercury during combustion. It's dangerous to mine and it's hard to transport. You can't use a pipeline. You have to use rails or truck. Nuclear has advantages, very little emission. A little matter can produce a lot of energy. Disadvantages would be accidents could be devastating, nuclear waste. They're expensive to build, and it's expensive to build reactors. So induced nuclear fission, fissure, break apart. A nucleus breaks apart into two roughly equal pieces plus neutrons. And then we've talked before that the first atomic bombs are just based on fission reaction. All commercial nuclear power plants are based on fission. This is an example of a reaction, but again, remember that what's actually produced will be a range of different products. Nuclear fusion, fused together, you combine two nuclei to form a larger one. Current nuclear weapons have conventional explosives to cause the fission reaction, and the fission reaction causes the fusion reaction. A lot more energy can actually be produced by the fusion reaction. Fusion is what powers stars. And then here is an example for a reaction for fusion. And so in 1953, Eisenhower said nuclear reactors will produce electricity so cheaply that it will not be necessary to meter it. Atoms will provide a safe, clean, and dependable source of electricity. Approximately 20,000 times as much heat energy is released from the fission of uranium fuel as from the equivalent amount of coal. Nuclear is one of the most expensive methods of producing electricity. Accidents to nuclear waste have caused worldwide concern. And so we could look at percent of power produced by nuclear power plants. Sorry, these percentages are a little bit old, but at one point during the oil embargo, France made a concerted effort to switch mostly to nuclear, and they were producing 69% of their electricity from nuclear power. Belgium, Sweden, all pretty high numbers. Japan at this time was about 30%. After the Fukushima, Japan cut their nuclear power generation greatly. England was about 18, and the US was about 18. And so it's kind of interesting. We can look at where nuclear reactors are, and so you see a lot in the US, a lot in Europe, not much in Africa or South America, Japan, China. And so there are a lot of nuclear power plants. Here is for the US. And so it's kind of interesting. Different countries actually use slightly different designs. And so there's 104 nuclear power plants licensed to operate in the US. 69 were pressure water reactor, 35 were boiling water reactor. They generate about 20% of the nation's electricity. And so the natural abundance of uranium-235 is about 0.7%. In a reactor, this fraction typically needs to be increased to above 3%. Now, the actual percent depends on what is the reactor design. And so you have to isotopically enrich the uranium-235 from 0.7 to something like 3%. Now, uranium-235 is the only naturally occurring fissionable material. And so what you can do is you can take uranium-235, you can make it into uranium hexafluoride, which is a gas, and then you separate it based on either diffusion or centrifusion. And so during World War II, the uranium-235 was enriched using large diffusion arrays. Currently, the technique is to use centrifuges. Uranium-235 can also be enriched using a breeder reactor, which produces more nuclear fuel than it actually consumes. The United States accused Iraq of obtaining aluminum tubes to centrifuge uranium hexafluoride, and has recently accused North Korea and Iran of using a breeder reactor to enrich uranium-235 for nuclear weapons. And so the uranium is mined and refined, converted to uranium hexafluoride, which is a gas. And then again, you can isotopically enrich, which just means that you try to separate out the uranium-235 from the other isotopes of uranium. And it used to be done using gas diffusion. Now it's mostly done using centrifuges. You then encase the uranium in solid ceramic pellets and then assemble them into fuel rods. And so the fuel rods, you have the uranium in the fuel rods. You also have rods that absorb neutrons. And so you control the nuclear reaction by controlling how many neutrons are floating around. The only difference between a nuclear reactor and a coal fire plant or a natural gas plant is how you heat the water. In a nuclear reactor, you use a nuclear reaction to heat the water. In coal fire plant, obviously, you just burn the coal to heat the water. The water becomes gas. The steam turns the turbines, and that's what produces the electricity.
Located in the nuclear core of a fission reactor are fuel rods, moderator and coolant fluid, and control rods. Each fuel rod contains tiny pellets of uranium dioxide. In these hundreds of fuel rods, fission occurs, producing an average of 2.5 neutrons per fission reaction. The fuel rods are surrounded by water, which acts as a moderator by colliding with the neutrons and slowing them to a low thermal level. The water absorbs the thermal energy, which is used to drive a steam turbine to generate electricity. The low-energy neutrons enter other fuel rods and collide with uranium-235 nuclei, creating additional fission chain reactions and the release of more neutrons. The amount of low-energy neutrons present is regulated by control rods made of boron, which are very effective at absorbing neutrons. These rods are raised out of or lowered into the core as needed to sustain the chain reaction at the desired level.
And so if you want to slow down the reaction, you put in the control rods. It starts to absorb the neutrons, and that will slow down the reaction. Now, a nuclear power plant cannot explode like a nuclear bomb. Again, for a power plant, you're looking at enrichment levels of like, say, 3 to 15%. For a nuclear bomb, you want enrichment levels on the order of 90-95%. And so the odds of a meltdown are 1 in 10,000 years. The plants have safe and reliable controls that are protected from any breakdown with 3 safety systems. And so this came from the Minister of Power for the Ukraine SSR, February 1986. A couple months later, April 86, the then leader of the former Soviet Union, Gorbachev, said, "Good evening, comrades. All you know that there has been an incredible misfortune. The accident at Chernobyl nuclear power plant. For the first time, we confronted the real force of nuclear energy out of control." And so this is what Chernobyl looked like after the accident. Now, the explosion was actually from steam heating up, producing a lot of pressure, and it wasn't a nuclear explosion in terms of a nuclear bomb. Again, for a power plant, you cannot have an explosion like in a nuclear bomb, but you produce a lot of heat. You can actually cause a lot of steam. You can actually produce an explosion. Now, it's kind of interesting. What happened was, at the time, the former Soviet Union was concerned that if they were attacked by another military power and it happened to disrupt power to the nuclear power plant, could they operate it safely? And so they wanted to do a test. So this was a safety test. And so the operators disabled 3 automatic shutdown mechanisms. When the reactor was shut down, there was a dramatic power surge and the few elements ruptured. The resultant explosion force of steam lifted the cover plate of the reactor, releasing fission products into the atmosphere. A second explosion threw out fragments of burning fuel and graphite from the core and allowed air to rush in, causing the graphite moderator to burst into flames. About 5% of the reactor core was released into the reactor. The graphite burned for 9 days, causing the main release of radioactivity into the environment. About 5,000 tons of boron, dolomite, sand, clay, and lead were dropped onto the burning core by helicopters in an effort to extinguish the blaze and limit the release of radioactive particles. And so basically they're trying to smother the fire. They're hoping the boron would absorb the neutrons, the lead would shield the radiation. The helicopter pilots died from radiation, and a dozen giant helicopters became so radioactive that they had to be abandoned. 31 people died in the course of the accident or sooner after. Some Ukrainian authorities say 5,700 have died of radiation-related illnesses. In the last 15 years, there's been a real and significant increase of thyroid cancer in children attributed to the Chernobyl accident. So there was a release of radioactive iodine, which is absorbed by the thyroid, which would cause the thyroid cancer. 135,000 people had to be evacuated from a 30-kilometer radius circle area around Chernobyl and the Pripyat, the city of Pripyat. And so this is what the deserted city of Pripyat looks like. Chernobyl is in the background. You can see it there. This is the biggest storage area for contaminated trucks and helicopters. And so here, this plume is a radioactive plume. And so you can see that Chernobyl is here. And so some of that radiation went this way, and then it got spread throughout Europe. The most radiological important nuclides detected outside the Soviet Union were iodine and cesium. And again, iodine is absorbed by the thyroid, and there's a link to thyroid cancer. And so you can see the area affected by the Chernobyl accident is really quite large. Most of Europe was affected by Chernobyl. Now, this is really pretty interesting. So at the Chernobyl site, there was 4 reactors. And so reactor 3 and 4 were next to each other. Reactor 1 and 2 were another building next to each other. And so then that accident occurred in reactor 4. And then they built a sarcophagus around reactor 4, trying to contain the radiation. And so in 1986, reactor 4 exploded. During the 1990s, there were $400 million of improvements. In 91, reactor 2 was shut down after the fire in turbine hole. 97, reactor 1 was shut down. In 2000, reactor 3 was shut down. Now, if you think about it for a minute, here you had explosion 86 in this reactor, and this reactor isn't shut down until 14 years later. Power is really important for society. 2008, all fuel rods should be removed. And it wasn't until recently that a new safe confinement structure was put into place. And so after they built the sarcophagus, they started seeing some cracks. It was losing some of its structural integrity. They built a new thing to confine the Chernobyl nuclear power plant. Now, one thing's kind of interesting. When Russia invaded Ukraine, they actually had their soldiers go to Chernobyl to actually try to take Chernobyl. And so their soldiers were in this radioactive region. The U.S. had its own nuclear accident. And so in 3 Mile Island, there was an accident in 1979. And so the accident occurred through a combination of mechanical and operator errors that allowed the reactor's radioactive core to overheat and partially melt. And so a pump failed in the reactor cooling system. The plant was automatically shut down. Pressure and temperature increased in the reactor, causing a pressure relief valve to open as it was designed to. The valve struck open for 2 hours. Water that cooled the core evaporated into the atmosphere. Operators mistakenly stopped the flow of emergency cooling water to the core. Temperatures increased in the reactor to the point where some of the uranium fuel melted and flowed to the bottom of the reactor vessel. When the new water was added, it shattered the extremely hot fuel rods. And so you can see the fuel rods here. It's kind of interesting. The president at the time, Carter, actually had worked on a nuclear submarine in the Navy, working actually with the nuclear power plant. And so most radioactivity from damaged fuel was prevented from escaping into the environment. Radioactivity was released into the environment, consisted primarily of noble gases, xenon and krypton. Nearly 10,000 samples of air, water, fish, fruits, meats, soils, and river sediment that were analyzed demonstrated that radioactivity released to the environment was small and will not have a detectable impact on human health. In March 2011, a 8.9 magnitude earthquake and subsequent tsunami overwhelmed the cooling system of a nuclear reactor along the Japanese northeast coastline. And so the nuclear power plants need power to keep all the safety measures going. And what you saw here was the earthquake saw a power disruption. And so after Fukushima, Japan shut down the nation's 54 nuclear power plants. 2013 reports highly radioactive, with some 160,000 evacuees still living in temporary housing. Some land will be unfarmable for centuries. The difficult cleanup job will take 40 or more years and cost tens of billions of dollars. And so fission, if you convert a little bit of matter into energy, you get a lot of energy. Problem is, some of the things you produce and use have half-lives of hundreds of thousands of years. Now fusion, if you could actually produce electricity from fusion, you would produce only radioactive particles that had half-lives that were much, much shorter. Reactors based on fusion would produce much less radioactivity. Reactors based on fusion would produce much less radioactive waste and could use seawater for fuel. Fusion is appealing because of the availability of light isotopes and because in general fusion products are not radioactive. The problem is that high energies are needed to overcome the electrostatic repulsion of the nuclei. The term thermonuclear is used for this reason. To achieve high enough kinetic energies needed for successful collisions, fusion reactors need to operate at temperatures over 10 to the 8th Kelvin. Now the only problem is there is no material that can withstand that high of temperature. And so you have to find a way of containing the plasma. For fusion to occur, you have to have temperatures of tens of millions of degrees. And so that means you're going to get a plasma. Examples of plasma include stars, fires, like neon lights. A plasma is a macroscopically neutral collection of charged particles. The bare nuclei have to approach each other within 10 to the minus 15th meters before the strong force can cause fusion. And so that's why you need such high temperatures for a fusion reaction. Now, to confine the plasma, you can try magnetic confinement, inertial confinement, or gravity. And so again, the plasma cannot touch anything because nothing can withstand such high temperatures. And so the joke is that fusion is the source of power for the future and always will be, but there has been some real significant advances in fusion in the last couple of years. In the last couple of years, for the first time, there was actually a fusion reaction that produced more energy than it consumed. I hope that helps.